school later this week, and John Schwartz. And she will provide us with introduction to supersymmetry for strings and branes. So,
well, thank you very much. Can you hear me? Yes. So today I will start the introduction on supersymmetry for strings and branes. I still want to do this one. Okay, now let me start this blackboard. So I will be giving the first in a series of lectures on supersymmetry and strings and branes. In total, there will be 4 lectures. I will be giving the first 2, and Melanie Becker will be teaching the last 2 towards the end of the week. So my part will be more at the introductory level, based on the book that Melanie and I wrote with John Schwartz. And in some points, I will go a little bit beyond what we discussed in the book. Now, so let me start with an introduction. To make contact between superstring theory and the real world, we have to understand the vacua of the theory. Now, of particular interest in vacuum construction are Dbranes, which are hyperplanes on which a string can end. On which strings can end. Since they can give rise to non-abelian gauge fields on the volume of coincident Dbranes or chiral matter. Then, also important in the construction of vacua of superstring theory are fluxes. So these are higher dimensional generalization of gauge fields. Like this, so we would have a one form, and fluxes would be maybe objects with several indices, tensor fields. Now, so why are fluxes important for phenomenology? Let me give you a motivation. So in one approach to obtain semi-realistic models of particle physics, we can, for example, start with a 10-dimensional heterotic string. And compactify on a space like this, where ME is 3 + 1 dimensional Minkowski space. And X is a Calabi-Yau threefold. For a particular choice of holomorphic vector bundle, which would be like a gauge field on this space X satisfying certain conditions, it is possible to obtain gut gauge groups, like, for example, so grand unified theory gauge groups, Like, for example, E6 SO10 or SU5. Now, however, besides the fields we are interested in having, like, for example, those non-abelian gauge fields over there or chiral matter, in most of these models we also get massless scalar fields in 4 dimensions. The so-called moduli fields. So some of these moduli fields arise from the deformations of X. We can, for example, take X, we can change its shape so that the Calabi-Yau space still stays a Calabi-Yau space, or we can change the size. Since the size is not determined, we get a whole family of solutions in 4 dimensions, and this is characterized by the fact that we get massless scalar fields in 4 dimensions. Well, these massless scalar fields can be ruled out experimentally, moduli fields can be ruled out experimentally, and moreover, it is unsatisfactory that if we cannot determine the size, we do not understand why the theory compactified in the first place. Now, it turns out that a compactification like this, on the other hand, is very special. So I talk about a metric, if I talk about a background like that, or about some gauge field. But in general, we also need to include fluxes in this background, which in this case would be 3-form flux. Be included. Now, it turns out that fluxes generate potentials for moduli fields while preserving supersymmetry in 4 dimensions. So once we include flux in such a compactification, we can induce potentials, generate potentials for moduli fields in 4D while preserving supersymmetry. So once fluxes are included in a compactification, they generate other effects that are important for phenomenology, some of which Melanie will explain in more detail in her lectures. So in the presence of flux, in general, the background is no longer going to be a direct product, but is going to be a warp product. There will be warp factors in the metric. Warp factor. If let me say schematically, we have some fluxes Fp that are not vanishing in the background. So let me give you an example of a warp metric, and an example that we are going to meet later, again during these lectures. Imagine that we have an 11-dimensional spacetime that takes the following form. Where this is some 3-dimensional Minkowski space. And this over here is a space X, which can be, for example, a Calabi-Yau fourfold. Now, in this metric, besides having these two pieces, we have this function over here, which is the warp factor, which is a scalar function depending on the coordinates of the Calabi-Yau fourfold only, of the coordinate of x. As Melanie will explain in more detail in her part of the lectures in the context of type 2b compactifications, in regions of large warping, a large hierarchy of scales can be generated in a natural way. Of scales can be generated in a natural way. So this provides one of the few natural solutions of the hierarchy problem in string theory, so why the weak scale is so much smaller than the Planck scale. So warping at this stage corresponds simply to taking not a direct product, so you say a product, but you have a scalar function over here that depends on the coordinates of the internal space. And that is something that is allowed if we want by the symmetries of the theory, so we don't want to single out any point or any direction in three-dimensional spacetime. This is still something that is possible. So, and another reason why this fluxes can be important, as we are going to discuss in more detail, in the presence of flux, it's possible to construct backgrounds which break supersymmetry and at the same time have a vanishing cosmological constant. So we are going to see examples of this in the context of M-theory, compactified or compactified on Calabi-Yau fourfolds. Now, so let me give you an overview of my lectures. So I will start with a discussion of string dualities and one of the simplest duality, namely Tduality, which can be discussed at the perturbative level. And which we will later use to construct low energy effective actions, and we will also use it in the construction of flux backgrounds. Then I want to review a few facts about low energy effective actions of superstring theory. And I want to mention a few additional dualities that we will later use. Then I want to discuss string compactifications and how moduli arise in some simple examples. Then I want to discuss in detail an example of a flux background where we are going to see explicitly how potentials for moduli fields are generated and how we can find solutions in which these moduli fields are massive and we preserve supersymmetry. M theory on Calabi-Yau fourfolds. Then I want to, as an exercise, to use most of the dualities we are going to learn about. I want to sketch some idea on how to construct flux backgrounds for heterotic strings. And maybe I finish with some conclusions. So while I give these lectures, I will be mentioning from time to time some little homework exercises that I will assign to you that you can try to work out, and maybe we can discuss some of those later after lunch. Maybe over lunch you can think about if you see how to solve some of those problems. I should mention, if you please feel free to ask if you have any questions. So let me start with a discussion of string dualities. So traditionally, there have been 5 consistent superstring theories in 10 dimensions with names like type 2A, type 2B, type 1, SO32 heterotic string, E8 times E8 heterotic string, and one theory in 11 dimensions, 11-dimensional supergravity, which is not a string theory. Now, even though the theories look very different at weak coupling nowadays we think that the theories are related through a web of string dualities. And one theory can be the strong coupling of the other. Like, for example, in this picture over here, 11-dimensional supergravity is believed to be the strong coupling limit of type 2A string theory when the string coupling constant becomes large. Now, the simplest example of string duality is Tduality, since it can be described using perturbative strings, using perturbation theory. And moreover, it appears for the simplest string theory we all learn about, which is the closed bosonic string. Now, for the closed bosonic string, Tduality says that if we compactify the closed bosonic string on a circle of radius r, so this is equivalent to a compactification on a circle with radius 1 divided by r. Now, evidence for such a duality appears first in the spectrum. So if we take the closed bosonic string and compactify it on a circle, let's say we have one dimension over here, which is going to be compact, like this. Let's call this direction x. Then the closed string can wind around the compact dimension like this. And associated to this winding, there's an integer that would be the winding number, which in this case would be equal to 2. Now, in general, to satisfy boundary conditions like this, we then take the string coordinate and demand the following boundary conditions. Let's say r is the radius of the compact dimension times w, where in the example there w is equal to 2, so this would be is an integer, which is the winding number. Now, to satisfy these boundary conditions, the zero mode piece of x needs to include the following term. So there can be a constant piece plus r times w times sigma, right? So if I shift sigma by 2 pi, I can satisfy those boundary conditions. Now, moreover, the entire string can have momentum in the compact direction. Since the direction is compact, it's a circle, momentum is quantized. And there's another integer in the theory that I'm going to call k. So k is another integer since momentum is quantized in the compact direction. And the zero mode piece of x then looks like this. And then there can be oscillators that I don't want to write out explicitly. A small exercise that you can read about more in detail in the book shows that the mass spectrum for such a string looks in the following way. -4 when NL and in R are integers. Now, this formula, this spectrum has a symmetry under the interchange of k and w and inverting the radius. Symmetric under interchanging of k and w and r with alpha prime divided by r. So that is Tduality. Yes.
What happens with the level matching condition?
Well, it gets interchanged, right? So k and w, they are integers, right? So they are in z, right? So then you. Now, there's an alternative way to express the statement of Tduality, which we will use in generalizations to open strings and also for the supersymmetric case. And it works in the following way. We split the string coordinate into left movers and right movers. And again, we are going to do this exercise only for the zero modes. And there's the following identity, so this would be the left movers. And then there are the right movers. Oops. Which shows that under this Tduality transformation, the left movers stay the same, they're invariant, while the right movers over here are going to flip the sign. Now, so we have just learned that the closed bosonic string is dual to itself if we compactify it on a circle. So it gets mapped again to the closed bosonic string. Now, if we apply Tduality to open strings, it turns out that Tduality exchanges strings with Neumann boundary conditions and strings with Dirichlet boundary conditions. Right? So we can see this with a small exercise. Imagine that we start with a string with Neumann boundary conditions, which would have a mode expansion like this. Remember that to have Neumann boundary conditions, we want the sigma derivative of x to be equal to 0 at the end of the string, let's say at sigma equal to 0 and pi, while here we want x to be constant at sigma equal to 0 and pi. Now, so if we have a string with Neumann boundary conditions, we would have an expansion like this. Oops. We go through the exercise again that we split this into left and right movers. Again, I'm just going to work out explicitly the zero mode piece. And I'm adding a constant x tilde here that cancels out of this expression. Plus oscillators. So we have our left movers and our right movers, and then we Tdualize. Tdualize by sending XL to XL and XR to minus XR. So then we get a dual field, which is equal to x tilde, now it doesn't cancel anymore, times sigma plus, and let me add again the oscillators, where the cosine is now exchanged by a sine. Now we can read off the boundary conditions of this field. Well, at sigma equal to 0, we get x tilde, and at the other, so one end of the string is held fixed, and the other end of the string, so the cosines are equal, the sines are equal to 0, excuse me, have these boundary conditions. Now remember that the coordinate is still compact, so momentum is quantized. P is equal to k divided by r, so we can rewrite the value of the coordinate at the other end of the string as 2 pi k times 1 divided by r, or in terms of the dual circle, which would have a radius r tilde, we would get this, where k is an integer. So if we go now back to our picture, what we now have in the dual variables would be something like this. So the coordinate is fixed in the compact direction at a point x tilde. The string winds around the compact direction an integer number of times. So in this case, k would be equal to 1. And this would be the dual radius. So the end of the strings, they are fixed. And this hyperplane where the strings can end is called a Dbrane. So let's say x tilde equal to x tilde in this picture is a p-brane. Now, in general, this p over here denotes the number of spatial dimensions of this hyperplane. P denotes number of spatial dimensions of hyperplane. So far, we have applied Tduality to strings propagating in flat space-time with one circle coordinate. Now, it turns out that there's a generalization. And Tduality, and we have seen that the radius of the circle gets inverted. Now, there's a generalization of this to general backgrounds characterized by a metric, a B field, and a dilaton as long as we have an isometry, as long as we have a circle direction isometry. Let's say in one of the directions, in the y direction. Now, so then it's possible to obtain the data of the dual background in terms of the original background. This carries the name Busher rules. So what I want to do is to quote here the result of this Busher rules, and in the homework session later today, we are going to discuss the derivation. So, derivation in the homework session. It's straightforward, it's just a little bit messy, so this is why I want to do it this afternoon. So the generalization is the following. The metric in the direction that has the isometry is inverted. So this is our rule that the radius goes over to 1 divided by the radius. But there's more information. So there are off-diagonal components of the metric. there's the dual metric. So we are going to use this a little bit later during these lectures. So this is why I want to tell you at least how this looks like. So Tduality also acts on the B field. And on the dilaton. Again, more about this in the homework session. Yes?
This is true for both type 2A and type 2E?
We are going to come to that. So at this moment, it's true for the closed bosonic string. We can still use these formulas, but in type 2A and type 2B, we are going to see that they are going to get interchanged. And there is more for type 2 theories. So let me review a few facts about low energy effective actions. So and let's go back to this picture of the different string theories and the dualities relating them. So low energy effective actions describe interactions of the massless fields in the spectrum of the different string theories. So let me start with type 2 theories, type 2. Now, so type 2 theories have an n equal to 2 supersymmetry in 10 dimensions, and there turn out to be two of them, type 2A and type 2B. So after gluing the left and right movers together, the massless bosonic fields in the spectrum arise from the Neveu-Schwarz and Ramon-Ramon sectors. Now, so the NS in the NS sector, so this is going to be the same for 2A and 2B. There is, after GSO projection, the lowest mass states are the following. So this over here are oscillators of worldsheet spinors now with Neveu-Schwarz boundary conditions acting on the Neveu-Schwarz vacuum. I think I want to tilt on the right-hand side. And I and J are SO8 vector indices. So if we multiply out two vectors of SO8, so we take the direct product, then we get a representation that is reducible in terms of a trace, which would be the dilaton, a representation which is symmetric traceless, which would be the graviton, and the antisymmetric representation, which would be the B field. So these are the massless fields in the NS sector, and they're the same for type 2A and type 2B. But in the Ramon-Ramon sector, they are different. Ramon-Ramon sector. So in the Ramon-Ramon sector, we would multiply 2 SO8 spinors of opposite chirality, SO8 of, let's say, opposite chirality. So this is what the plus and the minus denotes, opposite chirality. So there are in total 64 states, which we can reshuffle in the following way. So the product of two spinor representations decomposes into tensor representations. If they have opposite chirality, it works like this, into 56 and an 8, where it turns out that 56 corresponds to a three-form tensor, to a tensor with 3 indices, and the 8 corresponds to a one-form. Now recall that a vector naturally couples to particles world line, something like this. So a vector couples to a world line through an interaction like this. Right? So this is a one form that we can integrate over a world line. Now, it turns out that objects like this, like the 3 form over here, they couple to membranes. So there's a natural generalization of this, C3, where we would integrate C3 over the Wald volume of a membrane, which would be a Dbrane. Always remember that, so if we talk about a Dbrane, the Wald volume is going to be 3-dimensional. So that's a matter of notation. So this means that in the type 2A theory, we are going to, these Ramon-Ramon fields are going to couple to D2branes and D0branes electrically. So there will be electrically charged under this. And then there can also be the magnetic duals, which would be a D4 brane and a D6 brane. So in total, type 2A has even branes. So let's say in this direction. So type 2A has even branes. There's also the D8 brane, but it doesn't have propagating degrees of freedom. This is why it doesn't show up here. And then there's type 2B. So the Ramon-Ramon sector of type 2B in that case, we would take spinors of the same chirality. In the Ramon sector, and it turns out that the product of two spinor representations where both spinors have the same chirality decomposes into tensor representations as this, as a 35, a 28, and a 1. Now, the 1 corresponds to a 0 form. The 28 corresponds to a 2 form. Now, the 35 corresponds to a 4 form, but let's do the counting of degrees of freedom a bit more carefully. So if we have a 4 form, then the number of propagating degrees of freedom is going to be times 7 times 6 times 5 divided by 4 factorial, so it's an antisymmetric 4 form, right? But this gives 70 degrees of freedom, so we have to include an additional factor of 1/2 over here to get the 35 degrees of freedom. So, and this actually implies that on this 4 form we have to impose a self-duality condition. Namely, it's a 4 form that satisfies F5 is equal to star F5, where F5 is the field strength corresponding to this potential. Now, so this means that type 2B has dp branes with P odd, namely this one corresponds to couples to the D-1 brane, this one to the D1 brane, this one to the D3 brane. So there is D, let's write it in the same order. So D3, D1, and D-1 branes and incenton, and there are the magnetic duals. So 3 brane is dual to itself, there is the 5 brane, and there is the 7 brane. There's also an object that is called a D9 brane, also, which we are going to meet later again, D9 brane. So what such an object usually does is to impose some consistency conditions onto our theory, as we are going to later see. So Tduality for type 2 theories does the following. So remember the rule that under Tduality, let's say we are doing Tduality in the 9 direction, the left movers stay the same, and the right movers are going to flip the sign. Well, in the RNS formalism, Warchit supersymmetry requires that the corresponding spinors change the sign as well. So in the RNS formalism, we are going to have some Warchit spinors, and Warchit supersymmetry requires that the left movers then also stay the same, and that we get an additional sign for the right movers. So this changes the chirality of the right moving ground state in the Ramon sector, changes chirality of right moving ground state in the Ramon sector. So it exchanges type 2A and type 2B under Tduality. Now we can use what we have discussed so far to learn a few more details about how fields behave under Tduality. Namely, we can understand at least part of the Bouchard rules that apply to Ramon-Ramon fields, and the way to do that is to recall, but that will be enough for what I want to say in the rest of the lectures, recall that there is a coupling of the potentials to the dp brane that looks like this, that we have discussed already, which generalizes the coupling on a Wald line like this, Right, so we know that under Tduality, type 2A and type 2B get mapped to each other. So this means if I do a Tduality along the brane, this should get mapped to a dp minus 1 brane. So from here we learn, that Ramon-Ramon fields under Tduality in an isometry direction that I'm calling Y behave like this. So we are going to need this rule a bit later, so this is why I'm explaining it in detail. I1 to In. There is more stuff that is nonlinear in the fields, but this is all we are going to need later. So if we do an isometry in the direction Y, then this Ramon-Ramon field loses the Y component. And a field with no components in the Y direction would, after Tduality, so this is a mapping by Tduality, transform to a field with a component in the Y direction like this. Again, there's more stuff that is nonlinear in the field that we are going to talk about during the homework session, but this is all I will need for my lectures today. Now, what else? So low energy effective actions. Are going to be actions that describe the interactions between all these massless fields. Now, I don't want to present the details, but I want to mention a few facts about them. So you can read about them in more detail in the book. So details in book, if you wish. So the action is going to have several pieces. For example, the NSNS part where we would set maybe the Ramon fields all equal to 0, which is the same for type 2A and type 2B. There's going to be a part involving Ramon-Ramon fields, let's say kinetic terms for Ramon-Ramon fields. And there can also be the Chern-Simons piece. So Chern-Simons. Now, the way to construct these actions is to impose local supersymmetry. So we are talking about theories with n equal to 2 supersymmetry in 10 dimensions, and to supersymmetrize the theory. But it turns out that just with the tools that we have learned, we can determine some part of the action, and it's actually a fun exercise to try to work this out. Namely, remember that the difference between type 2A and type 2B appears in the Ramon-Ramon sector, and the Neveu-Schwarz sector is the same for the theories. So it's actually possible to determine the NS piece only from symmetries is determined by the following facts. It should be two derivative. It should be invariant on a coordinate transformation, diffeomorphism invariant. It should be invariant under gauge transformations acting on the B field. And the most important part that actually determines it, it should be invariant under Tduality. Duality invariant. So this means if you compactify it on, let's say, a circle bundle over some base, and then use those Boucher roots I presented, you should get the same result again. So it should be Tduality invariant. So I'm going to discuss this a little bit more detail again in the homework session today. And the result is that the Neveu-Schwarz part of the action is actually e to the minus 2 phi up to a total derivative, I should say, r plus where h is equal to dB. So again, that is actually a fun exercise to work out if you want. All right, now so the next theory I want to mention is M theory, which is the, let me say it in quotation marks, quantum theory of gravity, since we still have no definitive formulation for this, whose low energy limit is 11-dimensional supergravity. Limit is 11-dimensional supergravity. Now, the bosonic fields of 11-dimensional supergravity are simple. So there's a metric, and there's a 3-form. And the action is simple enough so that I can actually write it down here on the blackboard. So there's a kinetic term for the 3-form, DC3, and there's a Chern-Simons piece. Now, it turns out that type 2A supergravity can be obtained from 11-dimensional supergravity by compactifying on a circle. Type 2A supergravity can be obtained from 11-dimensional supergravity on compactified on a circle. So in general, so what we are going to do is to assume that the 11-dimensional metric is a circle bundled over some 10-dimensional base. And we have a scalar function here that I call phi. Now, so this over here is 10-dimensional metric. Now, so this scalar function here, the factors have been chosen for convenience. So phi is the type 2A dilaton. Phi is type 2A dilaton. And A over here becomes the type 2A Raman-Raman form. Raman-Raman 1 form. So this means in the mapping between type 2A and 11-dimensional supergravity, and this is a fact that we are going to use a bit later again. So the 11-dimensional metric gives rise, after compactification on a circle, to a 10-dimensional metric, the dilaton and the 1 form, the Raman-Raman 1 form, and the 3 form of 11-dimensional supergravity gives rise to a 3 form in 10 dimensions. And if one of the indices is in the 11 direction, it gives rise to a 2 form that is the NS2 form of type 2A. So these are the fields of 2A. And again, it's a fun exercise to take that 11-dimensional supergravity action plug in this circle bundle ansatz and this decomposition of the 3 form, and to work out explicitly the low energy effective action of type 2A. Homework would be determine the type 2A action starting with 11-dimensional supergravity. Yes.
Is there an intuitive way to see why, two of the NS sector fields and one from the RR sector fields actually become a purely geometrical M-series solution? This is a pure geometry. There's no free form, 11-dimensional free form.
Yeah, right. So this over here is the geometry. This is the background metric, and it's the most general ansatz that you can write down. And this over here is the way to decompose the 3 form.
Yeah, but if you forget about the 3 form for the time being,
yes,
the individual 3 form, then basically what you are left in the type 2A side is just the G, the phi, and the C1.
Yes.
Is there an intuitive way to see why 2 of the NS sector fields and one of the RR sector fields come together to give you this pure geometry?
Well, I mean, I don't know what you mean by intuitive. There's only one way you can decompose this, right? I mean, if you want to get a 1 form, what can you do? You need, so you're not going to get it from a 3 form, right? So because the 3 form is antisymmetric, so the only thing you can do is to have the components in, all the components in 10-dimensional spacetime, or one component in the 11 direction. And this way you get a 3 form and a 2 form. And you know type 2A has, I mean, just by counting the degrees of the forms, right? I mean, type 2A has a Raman 1 form, and you can only get it from the metric. I mean, from this Karuza-Klein ansatz. Now, so this is the 2-derivative action of 11-dimensional supergravity. Now, in addition to this, there's an 8-derivative term that we will meet again a bit later during this lecture when we discuss flux backgrounds. So 8-derivative. Correction to 11-dimensional supergravity, which is proportional to C3 wedge X8, where X8 is constructed from the curvature tensor in the following way. Now, so again, so this is an 8-derivative. Remember, each Riemann tensor gives you 2 derivatives, so this is an 8-derivative term. Now, again, we are going to meet this coupling again later when discussing flux backgrounds. Now, X8 has a few properties that I want to mention, which at this moment you can see as mathematical properties, but which will become important a little bit later. Namely, X8 is conformal invariant. So if so X8 is conformal invariant, so which means that if we rescale the metric by some function depending on x, X8 comes back to itself, which seems non-trivial because the Riemann tensor transforms in a complicated way. So you can check this either explicitly by simply computing it, or you can also use to prove this, you can use the fact that X8 can be expressed in terms of Pontryagin classes in the following way. I can simply continue writing here. So as P2 minus 1/4 P1 square, and Poitras classes are conformal invariant. The second property that is important is that the integral over a Calabi-Yau fourfold, so a space with certain properties, is the Euler character divided by 24. So this over here is Euler character. Now, the fast way to prove this is to rewrite these Pontryagin classes in terms of Chern classes. So P1 is equal to C1 square for a complex manifold, and P2 is equal to C2 square, C1, C3, plus 2C4. Calabi-Yau spaces have vanishing first Chern class, which allows us to express C4 as 1/2 P2 minus 1/4 P1 square. And according to the Gauss-Bonnet theorem for a complex manifold of complex dimension 4, the integral over C4 is going to be the Euler character. So integral over x8 is equal to 1 divided by 24, I think the numbers work out, times C4, and this over here is the Euler character. So that is chi divided by 24. So we are going to need this fact a bit later. No. Yes. Square. So it's an 8 form. Trace r to the 4, trace square, square.
This R is square or
Curvature 2 form. Right? Curvature 2 form, we take the trace.
Those things have 4 derivatives, not 8 derivatives.
Wait, we have 4 Riemann tensors. No, this is a derivative. We have 4 Riemann tensors, and each Riemann tensor gives us 2 derivatives, so we get 8. Right? Okay, good. All right, now, all right. Now, so the last theory I want to mention is type 2b. And there is one property I want to emphasize, which will also allow me to introduce what F theory is a little bit later, something that has been very popular in the last, let's say, years. So type 2b. So type 2b has a property that is important, namely, first of all, type 2b supergravity. Type 2b supergravity has an SL2R symmetry acting on the fields, SL2R symmetry. Acting on fields. So remember, SL2R are 2x2 matrices with real entries and determinant 1. So this means that we can write an SL2R matrix in the following way. A, B, C, and D are real numbers, and the determinant should be equal to 1. So A, D, they are real. And the determinant is 1. Now, so the way this SL2R transformation acts on the fields in supergravity is the following. It sends tau to A tau plus B divided by C tau plus D, where tau is a complex field, and it's given by a combination of the Ramon-Ramon zero form and the dilaton in this way. And the two forms transform like a doublet. So the two forms we can assemble into a two-component object like this. So there's the NS two form and the Ramon-Ramon two form. So and under an SL2R transformation, B gets mapped to lambda times B. The Einstein frame metric and the 4 form, C4, so both of them are invariant. Now, it turns out that in our quantum theory, charges are going to be quantized. And this breaks the SL2R symmetry down to SL2Z. So in quantum theory, SL2R is broken down to SL2Z. Now remember that there's a famous situation where SL2Z plays a role, namely the modular transformations of a torus. So imagine that we have a torus that we can construct like this by identifying opposite sides, and that is specified by a complex number tau, and this is 1. So remember that a modular transformation, for example, would be something like this. Color here. So this actually describes the same torus, and the tau parameter would be tau plus 1 in this case. So tau goes over to tau plus 1, and this corresponds to the same torus, so it's a modular transformation. Now, and this is not just an analogy, but there's a geometric interpretation for the SL2Z of type 2B. So it's probably wise, since it's 12:29 and 12:30 is a hard deadline, as I understand, so that we postpone this discussion. I want to finish it today, but maybe we do it in tomorrow's class. So in the next class, what I then want to do is to show how this SL2Z of type 2B theory can actually be mapped to the SL2Z transformation of a torus. Then we will get the chance to, so let me give you an overview of the next lecture. So we start with this geometric interpretation, and we are going to get a chance to introduce F-theory backgrounds. Then I want to discuss a few additional low energy effective actions, the low energy effective action of type 1 theories, a duality between heterotic strings and type 1 strings, compactification and moduli, and some flux backgrounds. So in the homework session later today, what we are going to do is to discuss some of the homework I've assigned. So again, if you would like to discuss about those over lunch, that would be good. Maybe you have an idea how to solve them. We are going to derive the Boucher rules, as I promised, and we are going to solve a few additional homework problems from the book, and you get also your chance to ask questions. And that's what I wanted to say for today. Are there any questions?
Are the actual forms in terms of curvature for the quadratic cousins, are those uniformly invariant, or are they only invariant in cohomology?
They are exactly invariant. So there is no total derivative. That's something that you can check. Either you can go to the old paper of Chern and Simons who have proven that Pontryagin classes are conformal invariant, or you can simply do the analysis yourself if you want. You simply work out the curvature 2 forms, you scale the metric. It's a lengthy computation, but that's something that is doable. More questions? Well, if not, see you guys later today.